Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Other Solar Cell Materials from the paper Energy Related Materials. The main points which will be covered in this module are a detailed study of semiconductor materials used in the fabrication of solar cell will be discussed. Second, how the structure and the properties affects the efficiency of solar cell. Third, what necessary treatment is required to reduce the cost and enhance the efficiency of solar cell using various semiconductor materials. So students, let us start with a brief introduction about the module. So first we'll discuss what is required for an ideal solar cell. It should be cheap, simple and abundant material, integrated large scale manufacturability. The cost should be very less and it should be long life. High absorption coefficient greater than 105 cm inverse with a direct band gap of 1.5 electron volt. Junction formation ability. It should have high quantum efficiency, long diffusion length, low recombination velocity. It should be abundant, cheap and eco-friendly material. They can be the convenience of shapes and sizes. It should be simple and inexpensive integrated processing or manufacturability. And it should have the minimum material, the minimum energy input. The energy payback period should be less than 2 years. It should be highly stable and long life greater than 20 years. Now, let us discuss the possible solar cell materials. What they can be? So, they can be single elements like silicon or carbon. They can be binary alloys or compounds like copper sulphide, copper oxide, copper carbon, cadmium telluride, cadmium selenide, gallium phosphide, gallium arsenide, indium phosphide, zinc phosphide, alpha silicon, SiH, dye-coated TiO2. Ternary alloys or compounds, copper indium sulphide, copper indium selenide and so on. They can be organic materials like semiconductor organics or polymers and dyes. Now let us discuss the crystalline silicon, that is the present scenario of crystalline silicon. Efficiency of single crystals silicon cells has been rising steadily to 25% as a result of better understanding of the junction properties and innovations in cell design and fabrication technologies. So the efficient gap between the best laboratory cells, submodules, modules and mass-produced modules varies with the maturity of technology and can be at least 10% lower at every step, so that the manufactured cell may be as low as 50% of the efficiency of the best laboratory cell. So the world photovoltaic production of 7900 megawatt in the year of 2009 is primarily around 93% based on single crystal and polycrystalline silicon. With increasing production of silicon photovoltaic from 200 kilowatt in 1976 to 6900 megawatt in 2008, the cost of solar cells has decreased from $100 to about $3 per wattage. With the existing technology and the material cost, the silicon solar cells cannot be decreased significantly. Their cost cannot be decreased unless the major innovations in the production of appropriate quality silicon, that is thin sheets, takes place. So the present day technology uses 8 inches or larger pseudo square of around 200 micron thickness with an efficiency of about 15 to 16%. The energy payback period of such cells is about 3 to 4 years. The module life is about 25 years. Specially designed silicon solar cells with efficiency 18 to 20% are being manufactured on a limited scale for special applications, example for concentration. Polycrystalline silicon solar cells with efficiency 12 to 14% are being produced on large scale. Specially designed thin films silicon solar cells with efficiency of about 12% have been fabricated on a lab scale. Production of hybrid thin film silicon cells on megawatt scale is being pursued. Polycrystalline silicon. Single crystal silicon solar cells. They give quite high efficiency of the order of 16% under AM1 conditions. Also, these cells are quite reliable and stable under terrestrial and space conditions. However, the high fabrication costs of single crystal silicon solar cells limit their application for terrestrial applications. Hence, research is being conducted both on the polycrystalline silicon and amorphous silicon materials as the key candidates for solar cells in thin film form. Now, it has been discussed earlier that the polycrystalline silicon can be acquired in the form of thin ribbon drawn from molten silicon bath, or allowing the silicon vapors to deposit on a cool flat surface or solid block. If the molten silicon cools under the normal conditions, then the resulting block contains the myriad of microscopic crystals. If the molten silicon is cooled very slowly, then crystallites of larger size are obtained. The polycrystalline silicon is in the form of granules, and the size of crystallites mainly depends on the cooling conditions. The silicon solar cells made from polycrystalline silicon are low cost but are of low efficiency, also from 5 to 10%. Significant losses of photo-generated electron-hole pairs are generated at the grain boundaries, and they are known as short circuiting. Therefore, the grains or the crystallites should be large in order to get the better performance. So the figure shows the cross section of the polycrystalline silicon solar cells. There are three groups of solar cell structures which are prepared by using polycrystalline silicon. These cells are p-n junction cells, metal insulator semiconductor MIS cells, and conducting oxide insulator semiconductor cells. In a p-n junction solar cell, the polycrystalline silicon film can be deposited by any one of the techniques like dipping, chemical vapor deposition, and vacuum evaporation on various substrates like graphite, glass, ceramic, sapphire, metallurgical grade silicon, and metal. The idea of a metal semiconductor junction is quite attractive since it simplifies the manufacturing process and is of low cost. These cells shows a similar short circuit current ISC and low open circuit voltage VOC as compared to p-n junction cells, resulting in low cell efficiency. By inserting a very thin insulating layer in between the metal and the semiconductor, this problem can be solved, and the solar cell is named as metal insulator semiconductor solar cells. So by making the insulating layer very thin, VOC can be increased and can become almost equal to the p-n junction cells. Now there is a new concept known as the epitaxial solar cell, in which the active layer is a thin pure silicon layer which is deposited on a substrate which can be very pure and have given encouraging results, and the cells of highest efficiencies of around 9 to 12%. In the conducting oxide insulator semiconductor cells, a window semiconductor is used over an active semiconductor substrate. This thin film oxide window, which has high transmittance for solar cell radiations and high electrical conductivity, which act as the anti-reflective coating. Several window materials are tin oxide, indium oxide, and indium tin oxide have been tried with different deposition techniques such as spray deposition, chemical vapor deposition, and electron beam deposition. Amorphous silicon solar cells. Amorphous silicon has very high absorption coefficient over the major portion of visible spectrum, making it extremely thin film device possible leading a low material cost. Low temperature deposition process can be used to uniformly coat large areas. The deposition technique and the byproduct of the technique are environmentally benign, making it a truly green manufacturing process. The optical band gap of 1.7 electron volt lies close to the peak of 1.5 electron volt where high efficiencies are expected. Monolithic integration of individual cells is simple and is done by selective laser ablation, allows for module voltage optimization. Silicon and hydrogen, they are abundant. Material can be doped P or N type with boron or phosphorus respectively. The material possesses the necessary electron and hole transport properties for PIN type solar cells. Amorphous silicon cells. A alpha silicon solar cell is prepared in multi-chambered cell showing the higher efficiency compared to the single chamber, and it can be fabricated basically with four structures. First is heterojunction, second metal insulator semiconductor MIS, third PIN devices, and fourth is Schottky barriers, and these are all shown in the figures. Now let us discuss these one by one. An alpha SiH Schottky barrier solar cell was first reported in 1977 with a conversion efficiency of 5.5. Later, in 1978, a group of scientists at the Osaka University, Japan, fabricated the alpha silicon solar cell by producing a heterojunction solar cell with a construction of ITO PIN stainless steel with an efficiency of 4.5%. These types of amorphous solar cell structures are presently used because they can be produced on large areas with good reproducibility, and the parameters responsible for the cell behavior can be controlled. The first heterojunction solar cell was produced by depositing the amorphous silicon on glass coated with either tin oxide doped with antimony or indium tin oxide, also shown in the figure A. The most suitable heterojunction solar cell was first prepared by depositing an undoped SiH layer on ITO or tin oxide antimony coated glass substrates, where a thin p-doped alpha SiH layer is used to make ohmic contact with evaporated aluminium contact. This cell design provides a VOC of 0.43 volts, ISH of 10 milliampere per centimeter square, eta FF of 0.28 and eta S of 1.2% under AM1 conditions. The next is the PIN junction based alpha silicon solar cells, They are most suitable solar cells for commercial production, which shows good performance, and they can be produced in two types of structures. These are shown in figure B. In the first type, the substrate is of ITO coated glass, on which first a p-type alpha SiH layer is deposited, then a layer of intrinsic alpha SiH layer is deposited, and then finally on the backside of PIN structure as the and is deposited, and then finally a layer of N-type alpha SiH layer is deposited. A titanium aluminium metal layer is deposited on the backside of PIN structure as the collection electrode. This platinum SiO2 PIN alpha Si silicon solar cell has given the VOC of around 0.77 volts, ISH of 7 milliamperes per centimeter square, eta FF of 0.6 and eta S of 3.3% under AM1 condition. In the other type of PIN junction alpha silicon solar cell, first a layer of boron doped alpha SiH is deposited on steel, then a layer of undoped alpha SiH is deposited, and over to it is deposited a layer of N-doped alpha SiH. Finally, a thick layer of ITU is deposited on the N-type layer, which act as a conducting electrode and as well as the anti-reflective coating. The Schottky barrier alpha SiH solar cells can also be fabricated easily, whereas a thin layer of p-doped N plus alpha Si on stainless steel structure, then a layer of undoped alpha SiH, then a Schottky barrier metal, then a palladium contact pad on one edge of the platinum layer, and finally a thick layer of zirconium oxide as an anti-reflective coating. This is shown in figure C. This cell has given a VOC of 0.8 volts, ISH of 12 milliamperes per centimeter square, eta FF of 0.58 and eta S of 5.5% under AM1 condition. This Schottky solar cell structure has many advantages over other structures, both the barrier height and the field region width can be improved by introducing an insulating layer in the Schottky barrier and lower work function of metals which are less expensive than platinum or palladium. Stacked alpha silicon or alpha SiH cell. As discussed earlier, since a single junction alpha silicon solar cell, the incident photons with energy less than Eg are not utilized and they goes wasted as the heat, providing low cell efficiency. So the idea of using long wavelength photons by a highly reflective random surface was first proposed by Bohr and Van Strip, which was later proved by Exxon Group. The photons with longer wavelength can be absorbed via utilizing multi-function cell or stacked junctions where semiconductors of different energy gaps are stacked on top of each other with decreasing band gap order. Studies on stacked alpha silicon cells are under progress at SERI USA, and the structure being studied is shown in the figure. In this structure, three stacked cells using NIP configuration are considered ideal from practical consideration. The first two cells are standard alpha SiH acting as intrinsic layer, whereas the third or the last layer is an alloy of silicon, germanium, and hydrogen, which is the alpha SiGeH. Here, alpha SiH cells capture most of the blue-green end of the spectrum, whereas this alpha SiGeH cell captures the red part of the spectrum. Theoretically, this three-layered structure with the band gaps of 2, 1.7 and 1.45 electron volts respectively can result in the efficiency of around 24%. Now let us discuss about the gallium arsenide solar cells. The direct band gap of gallium arsenide can absorb the sunlight very quickly after entering it. And the deposition techniques to deposit the gallium arsenide includes the molecular beam epitaxy MBE, MOCVD, CVD and LPE. Homo, hetero, stacked, multi-junction, tandem junction and PEC are possible in the case of gallium arsenide solar cells. The efficiencies for the homo junction is around 23.3%. For aluminium gallium arsenide silicon, it is around 26.9%. Aluminium gallium arsenide gallium antimony is around, that is tandem structure, 32.6%. Gallium arsenide indium gallium phosphide stacked indium gallium arsenide 30%, and indium gallium phosphide, it is around 33%. So the junction formation is straightforward. There are various types of junctions possible which are suitable for stacked cell applications, stable cell which is good for high temperature applications, expensive materials and processing. It has limited laboratory batch size production for a specialized application. Cadmium sulphide or copper sulphide solar cells. The photovoltaic effect in cadmium sulphide or copper sulphide was first discovered in 1954. Generally, the cadmium sulphide cells are developed by the process called as Cleveet process, where the cadmium sulphide is vacuum evaporated onto the metal sheet or metal covered glass, where it gets deposited to a thickness of only 20 micron or so on, and it has been shown in the figure also. This layer has crystallites of diameter of about 5 micron, and the layer is then dipped into cuprous chloride solution for 30 seconds, which substitutes copper for cadmium in a thin surface region about 1000 to 3000 angstrom thick, resulting in a cadmium sulphide or copper sulphide heterojunction. Finally, the grid contacts are made onto the lower and the upper surfaces. The copper sulphide is a p-type material with a band gap of 1.2 electron volt, whereas cadmium sulphide is an n-type material with a band gap of 2.3 electron volts. So the cells produced in this way gives the efficiency of about 5 to 9%. Cadmium sulphide or copper sulphide cells are the simplest devices which perform almost anomalously. However, the mechanisms of their good performances are not well characterized as of silicon and gallium arsenide. The response of cadmium sulphide, copper sulphide involve several non-linearities. Compared to silicon solar cell, the cadmium sulphide copper sulphide solar cell is basically not the copper sulphide. By replacing the copper sulphide with copper zinc sulphide, a copper ZS solar cell is much thinner and is made from polycrystalline material. There are several advantages of cadmium sulphide copper sulphide solar cell, such as easy fabrication, can be mass produced, large area cells can be made in rectangular shape, reducing the special losses, and energy consumption in the cell production is low. Some of the disadvantages of cadmium sulphide copper sulphide cells are low efficiency compared to silicon solar cells, deterioration due to moisture and air, and cadmium is also quite toxic and is not abundantly available. Cadmium sulphide, copper, indium selenide solar cells. In this type of solar cell, the structure is considered as a heterojunction with cadmium sulphide as a window material and copper indium selenide. Photoluminescence spectra of copper indium selenide shows the levels at the sites occupied by copper atoms, which lead to a p-type conductor in the copper-rich phase, while the n-type conduction in the indium-rich phase is observed. This complex nature may lead to buried homojunction at the interface between cadmium sulphide and copper indium selenide. Thin film deposition using multiple source evaporation results in high quality films with grain sizes of about 2.5 micron. The moly film, which serves as a back contact, is deposited at the temperature range of about 300 and 450 degrees Celsius. The schematic structure of cadmium sulphide copper indium selenide thin film solar cell is shown in the figure. In order to avoid interdiffusion, the cadmium sulphide film is deposited at lower substrate temperatures. Heat treatment in oxygen is an essential step in fabrication in order to get the excellent cell performance. So the highest value of efficiency which has been reported for cadmium sulphide, copper indium selenide thin film solar cells is of about 12.5%. The stability is the excellent feature of cadmium sulphide copper indium selenide solar cells, which does not demand any special protection and encapsulation. Hence, it is believed, therefore, that this type of solar cells provides a viable alternative to crystalline and amorphous silicon cells. Further, due to lower band gap of copper indium selenide, the solar cells based on this provides the substantial potential for use in tandem structures. Cadmium telluride, cadmium sulphide solar cells. Cadmium telluride, it has various advantages for its use in thin film heterojunction devices over other solar cell devices. It has a direct band gap of nearly 1.47 electron volts, which matches with the sun's spectrum, and hence it can be used as high efficiency photovoltaic material. Furthermore, this is the only material which can be made highly conductive in both the N-type and P-type. Also, the high absorption coefficient of about 10 to the power 6 centimeter inverse indicates the huge absorption of incident light within a thickness of 1 micron. Very little work has been reported using single crystal cadmium telluride pin homojunction cell. Few scientists around the globe have already reported an efficiency of 13% in the case of single crystal homojunction cell by using a P-type cadmium telluride, which is grown epitaxially on the N-type cadmium telluride. However, cadmium telluride based heterojunction solar cell structure are the promising candidate, which uses a wide band gap, high conductivity window layer, etc. In this case, the crystal or polycrystalline cadmium telluride wafer are used, over which there is a thin film window layer of materials like cadmium sulphide, ITO, zinc oxide, zinc selenide, tin oxide, cadmium oxide is deposited. Now, the high efficiency cadmium telluride based solar cells were made by using single crystal cadmium telluride, over which various window materials are deposited by vacuum evaporation, spray pyrolysis, RF sputtering techniques. Experimentally, it has been found that the deposition of a cadmium sulphide layer on a P-type cadmium telluride single crystal induces a shallow cadmium telluride PN junction. Solar cell based on such structures exhibits the efficiency of up to 12% and could be expected to represent the optimum structure. The situation in the most successful thin film cells, however, it is not completely clarified so far. So students, let us summarize what we have learned in this module. There is a large range of materials that may prove viable alternatives to the single crystal silicon that forms the basis of the present solar cell industries. Gallium arsenide is a semiconductor with well-developed technology and has a nearly ideal band gap for solar photovoltaic energy conversion technology. However, the high cost of the material is a major hurdle. Copper sulphide, cadmium sulphide, they can be easily fabricated on small grained polycrystalline cadmium sulphide. It is potentially a low cost technology. The difficulty of achieving the 10% efficiency on a production basis, combined with stringent encapsulation to prevent the degradation, may prevent its widespread use. Polycrystalline silicon has disadvantage that large grain size is required. Thank you.